In this section, we're going to take a look at the idea of the definite integral. And again, this should also be a refresher from your Calc 1 experience. If it's not, you might want to go review Calc 1 and try to do some other things. So the big idea of this section is that we want to calculate the concept of signed area. So we're going to have a function. And with regards to that function will at some points be above the x-axis and at some points be below the x-axis. If we take the area between our function and the x-axis, signed area means that if our function is above the x-axis, the area between the function and the x-axis will be counted as positive. And if our function is below the x-axis, the area between the function and the x-axis will be counted as a negative. So signed area is often referred to as area under the curve because the orientation of the area under the curve when our curve is above the x-axis is positive. But again, if it drops below the x-axis, we're counting that area between it and the x-axis as negative. Now, in certain instances, it's pretty easy to find the signed area. So imagine that I have a line that goes from the origin to the point 6,3. And I want to find the signed area of that line. Now, the signed area is going to be this area shaded in red. And in this instance, since our line is always above the x-axis, this area is going to be counted as a positive. And we can visually see that this area is just a triangle. And the area of a triangle is 1/2 times the base times the height. The base length here is obviously 6. The height is 3. It's a right triangle. So 1/2 times 6 times 3 is 9. So once again, we're calling it the signed area of this line. Signed area of the line. Again, in this case, I can just use the area of a triangle, 1/2 base times height, which is 1/2 times 6 times 3, which becomes 9. So the area of the triangle, which is the signed area of this curve, this line, is 9 in this case. Now, in other cases, let's say we're looking at this line. Again, this red line. Now, I've highlighted the signed area. So you can see that the signed area is a combination of these two. But this horizontal line is the x-axis. And for part of our signed area, we have our curve is above the x-axis, our line is above the x-axis, and for other part, our line is below the x-axis. Now, hopefully we can see that the amount of area above the x-axis is bigger than the amount of area below the x-axis. Again, this time we're going from 0 to 6. So if I look at this signed area, it will be positive. And if I wanted to calculate it, I could. I could say, well, this is a triangle whose base is 4 and height is 2. So if we take a triangle whose base is 4 and whose height is 2, that's an area of 12. This triangle has essentially base of 2 and height of 1. Oh, I'm sorry, not height of 6. So, excuse me, base of 4, height of 2. Base of 4, height of 2 gives you an area of 4. I misspoke earlier. So, the bigger triangle is area 4. The smaller triangle, base of 2, height of 1. 1/2 times 2 times 1 is 1. So this area is 4. This area is 1. Therefore, the total signed area is going to be 4 minus 1, which is 3. So we're going to get a positive signed area because more area is above the x-axis than below. And in this particular case, we can see that the area is 3, 4 minus 1. We can take a look at another example. Let's take this line that goes from 0, -3 all the way to 4, 1. And we're looking at it from 0 to 4. Now, in this case, the signed area is going to be negative because the part that is underneath the x-axis is bigger than the part that's above the x-axis. So this signed area is going to be negative. And if you wanted to calculate it, you could. This is 3, a base of 3, height of 3. So that's going to be 4.5. And this is a 1 by 1 triangle. So that is 1/2. So total signed area would be a -4 because that's a -4.5 and a positive 1/2. So there we go. Now, we can also determine positive or negative signed area just by looking at it. We don't have to calculate everything. If we look at this curve, this is not a straight line. This is some sort of a cubic equation. And we can see that the signed area from -2 to 2 gives us these two shaded regions, which appear to be the same size. Since one is above the x-axis and the other is below the x-axis, and they appear to be the same size, the total signed area here would appear to be 0. So neither positive nor negative. Again, to calculate the actual signed area of this guy and the actual signed area of this we need some new skills, which we'll see later, but that's the idea. Now, as we saw, we can use geometry sometimes. When we have things that are rectangles or triangles, or if I had a perfect circle, then geometrically I know the formulas for areas of rectangles and areas of triangles and areas of circles. And that's what we're kind of going to use to begin with. So the goal is to calculate the signed area of a closed interval. And in certain circumstances, we can use rectangles and triangles to find that signed area exactly. So let's do an example. Let's take the line f of x equals 2x minus 1 on the interval from 0 to 3. We're going to find the signed area of that function on the interval from 0 to 3. That closed interval from 0 to 3 means that we're starting at x value of 0 and ending at x value of 3. So let's go ahead and graph this function over that interval and visualize the signed area. All right, I have graphed this line on the math tool Desmos. And Desmos is a really nice math calculator. So I'm going to use that a lot. But you can see that this line, f of x equals 2x minus 1, does this. Now, we're actually only interested in the line between the x values of 0 right here and 3. So we're interested in this section of the line from 0 to 3. You see that part of the line is underneath the x-axis, and part of the line is above the x-axis. Where it crosses the x-axis is the point 0.5 comma 0. So what I'm going to do is I'm going to break this up into two parts. One triangle that's below one triangle that's created from being our line part being below the x-axis, and one triangle from above the x-axis. So there we go. The triangle that's below has essentially height of 1 and base of 1/2 or 0.5. It goes from 0 to 0.5. The triangle that's above the x-axis goes from 0.5 to 3, so it has base of 2.5, and its height goes from 0 up to 5. So it has height of 5. So that's all we need to do to calculate the signed area. Signed area is going to be this triangle, which I have in red, again, for positive. So I'll call it the positive triangle, minus what I'll call the negative triangle. That's the area for the positive triangle and the area for the negative triangle. So the signed area, like we said, as far as the smaller triangle, or excuse me, let's do the positive triangle here, goes from 0.5 to 3. So its base is 2.5. And the height goes from 0 to 5. So its height is 5. So 2.5 times 5 times 1/2 gives you a 6.25. I'll write that down on the next line. And then the smaller triangle, obviously 1/2 base times height. The base here is 0.5, going from 0 to 0.5, and the height is 1. So the total signed area there is 6.25 minus 0.25. So the signed area is exactly 6. So that's the calculation of this signed area using geometry. It's just triangle minus triangle in this case. Now this brings us to the concept of the definite integral. We looked at indefinite integrals in the previous section, which had to do with antiderivatives. It turns out definite integrals deal with the signed area. The definite integral of a function on a closed interval from a to b is the total signed area of the function on that closed interval from a to b, excuse me. And we draw it just like the integration, but we put little bounds below and above the integration symbol to show that we're going from A to B. Okay. So A and B are what we call the bounds of the integration. So this is a definite integral. And the definite integral is just the signed area of that function between x values of A and B. Now you may say, well, how is this connected to the antiderivatives? Well, this is connected with the antiderivatives. We'll see that in the next section, in the next video. So if we were asked to calculate this, the definite integral from 0 to 3 of 2x minus 1, we've actually already done that. When we found the area, or the signed area, I should say, of f of x equals 2x minus 1 on the closed interval from 0 to 3, we found that to be 6. So this integration is just 6. I won't redo my calculations from before, but basically, those calculations mean that this definite integral is simply 6. And we calculated that using the geometry from before. Positive part minus the negative part. Positive area minus the negative area. So there you go. That's how we could calculate a definite integral. Now, obviously, we can do that in a lot of different cases. We can break it down geometrically in various different cases. So let's take a look and try to calculate the definite integral from 0 to 2 of x plus 3 with respect to x. So I'm going to graph the line y equals x plus 3, or f of x equals x plus 3. You'll notice that line goes through the point 0, 3, has slope 1, and we're trying to integrate, take the definite integral from 0 to 2. So we're taking that section of the line. So we want to find the area underneath that line, but above the x-axis. I've now shaded that in red. Now, what we can do for this one is we can break this up into a triangle, that triangle, and a rectangle. And we know the formula for the area of a triangle. We know the area formula for a rectangle, width times length. And if we use those two formulas, add up triangle area plus rectangle area, then we're good to go. So let's go ahead and do that. Let's break it up into triangle plus rectangle and then add it up. By the way, I'm saying that there's no area underneath. There's no place where our line is underneath the x-axis. So this area is going to be all positive. All right, so here's our picture. Let's make that a little bit smaller. There we go. And we want to find the signed area underneath y equals x plus 3. So what I'm going to do is take the area of that triangle. That triangle has base of 2, height of 2. So area of a triangle is 1/2 base times height. And then add the area of that rectangle that I drew. That rectangle would have width of 2, height of 3, or length of 3, width of 2, length of 3. Area of a rectangle is width times length. So that's just going to be 2 times 3. And when we add those things together, we're going to get, well, 2 plus 6 is 8. So we got the triangle area, 1/2 base times height. The rectangle area, which was 2 times 3. And together, that gave us an 8. So the definite integral here, the signed area under the curve, becomes 8. Now, these two examples, this one and this one, were very nice to find the definite integral because they worked out geometrically into either adding or subtracting nice geometrical objects like triangles and rectangles. And oftentimes we can do that. We can calculate definite integrals using ge geometry, basically, using rectangles, using triangles, using maybe other things like circles. And we can find the area by just utilizing the geometry behind it. And we can do clever things as well. One clever thing we can do with any definite integral is to break it into sections. So if we have like a piecewise function, we could break it into pieces, break it into sections where one section looks like a triangle, one section looks like something else. And so if we want to integrate from A to C, we could first start by integrating from A to B, and then from B to C, and together, when we add those two together, that'd be like integrating from A to C. So we can break into pieces as well if we want. But no matter how hard we try, in some cases, when we have curved functions, or when the graphs of our functions are curved in ways that we can't deal with geometrically, things don't work. Well, I should say geometry just doesn't cut it. So in many cases, using standard geometric tools of finding area don't work to find the signed area because some of these curves are really ugly. Think back to the picture we had before. If I wanted to find just one of these blue pieces, I'd say, well, these aren't straight lines. So it'd be very difficult to find using triangles and circles and squares and things like that, rectangles. So again, sometimes definite integrals are hard to do with geometric tools. Okay. And here's another one. This is just a parabola integrated from 1 to 4, the x squared plus x. Let's go ahead and graph that just so you have a visual. So again, I've integrated that, or is it not integrated? I've graphed that on Desmos. And if we're looking at from 1 to 4. We're going to start here and we're going to go all the way to 4. 4 is going to be way up there. Turns out gets to that point. Oh. And so basically we're looking at this section. And if we're looking for the area under the curve on that section, we're looking at this signed area. Now, obviously, this curve is not a straight line. It's bent, it's parabolic shaped. And so our geometric tools are not going to work really nicely. So this one would be really hard to calculate using those geometric tools. Now, you could sort of break it down and get pretty good approximations. And in fact, that's the theory behind how to actually calculate a definite integral is to get better and better approximations. But that's not in this section. I just wanted to point that out. We'll calculate this. We'll get the tools to calculate this in the next section that we go over. Now, I just want to note something that in every case that we've had so far, when we've integrated a function from A to B, our definite integrals had the smaller number below and the larger number above the integration symbol. That's how the standard does it. That's how we do it always. I shouldn't say always. That's how we usually do it. Okay. This is the way the signed integral, the signed area works with the definite integral. We always assume that A is the smaller one. If we flip that, if we flip the bounds, then all we've done is, so if we put the B on the bottom and the A on the top and B is bigger than A, then basically we just found the negative of the signed area. So everything we counted as positive before, now we count as negative. Everything we count as negative before, we can now count as positive. We don't do that very often in this class because it doesn't come up in a lot of applications. In certain cases it will, but I just wanted to point that out. With signed area, we are always associating that signed area with the definite integral, where A is the smaller number, B is the bigger number, A is on bottom, B is on top. If you flip it around, then you get the negative of the signed area I was talking about before. So that's the idea in this section. This idea of definite integrals giving a signed area. We can use geometry on certain curves, certain functions, which give us nice straight lines. But when we don't have straight lines, we have to get some other tools. And that's what the next section will be about.